At this point, it would be appropriate for us to do a few examples of taking derivatives using the techniques that we've talked about. Let's consider this function y is equal to the square root of x plus 1 over x, and we want to find the dy dx, or we want to find the first order derivative of y with respect to x. Well, remember that the power rule works for powers of variables that are in the numerator, so let's rewrite this in terms of powers of variables in the numerator. So we have the square root of x. Well, the square root of x is really x raised to the power 1/2. All right, plus we have 1 over x. Notice that's x to the first in the denominator, but again, the power rule deals with powers on variables in the numerator, so we'd have to rewrite this as x to the negative 1. All right, now if I want to take the derivative of y with respect to x, I'd be taking the derivative of this expression, which, according to our properties of definition, is the derivative of the sum, so I can take the derivatives independently. And now I can simply use the power rule to take the derivative. So the derivative of x to the 1/2 is, well, bring out the old exponent, and the new exponent is 1 smaller. So 1/2, make 1/2 1 smaller, subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. Plus the same thing, take the old exponent out in front, and the new exponent is 1 smaller. Negative 1 minus 1 is negative 2. So this would be then 1 over 2 times, all right, we'll put the x to the negative 1/2 in the denominator so that its exponent will be positive. All right, minus 1 over, we'll do the same thing here with this x to the positive 2 in the denominator. And now remember that x to the 1/2 is the square root of x. So this would be 1 over 2 times the square root of x minus 1 over x squared. And this will be the function that will give us the instantaneous rate of change in y with respect to x. It will give us the slope of the tangent lines to y equals to our function y, the graph of y. All right, let's consider this example. All right, find d squared y dx squared. All right, the second derivative of y with respect to x for the function y is equal to the quantity x to the third plus 1 squared. We'll soon have a way to deal with this a little more directly, but let's rewrite this. This would be 3x squared plus 1 times 3x squared plus 1. And if we multiply this out, we're going to get 9x to the fourth, all right, plus 3x squared plus 3 more x squared is plus 6x squared plus 1. Okay, now to take the derivative of y with respect to x, well, first of all, I have to take the first derivative. Okay, I'm going to show you all the nitty-gritty now. We'll have the derivative with respect to x of 9x to the fourth plus 6x plus 1, which is the derivative with respect to x of 9x to the fourth plus the derivative with respect to x of 6x plus the derivative with respect to x of 1. And this, of course, would be 9, taking out, we can take the constant factors out, 9 times the derivative with respect to x of x to the fourth, plus 6 times the derivative with respect to x of x, and I'll call that x to the first, plus 1 is x to the 0. So so we'll have 9 times x, the derivative of x to the fourth. That would be 9 times 4x to the third using the power rule. All right, plus 6 times 1x to the 0 plus 0 times x to the negative 1. And notice this will be 36, 9 times 4, x to the third, plus 6 times 1, plus 0. So this would be the first derivative. Okay, to take the second derivative, we'll have to take the derivative of this first derivative. All right, that would be 36. I'll not go into quite as much detail here. Times the derivative with respect to x of x to the third, plus 6 times the derivative with respect to x of x to the 0 power. And this would be 36 times 3x squared using the power rule, plus 6 times 0x to the negative first, again using the power rule, which is 36 times 3 is 108, 108x squared, okay, times, or excuse me, plus 0. So that would be the derivative of the second derivative of that expression. Let's take the derivative now of f of t is equal to t to the third, or t squared plus 1 all over t to the third. Again, we'll have to express variables in the numerator as powers in the numerator. So let's rewrite f of t as t squared over 3t, right, plus 1 over 3t. This can be thought of as, notice, t squared over t, one of the t cancels, and I'd have 1/3 t to the first. All right, plus here t in the denominator, it's t to the negative first in the numerator. Remember, the power rule works on powers in the numerator, so this would be 1/3 times t to the negative first. Now the derivative, using the Newton's notation, the derivative of f of t is going to be 1/3 times the derivative of t to the first plus 1/3 times the derivative of t to the negative first. And this will be 1/3 times, using the power rule, 1 times t to the 0 plus 1/3 times, again using the power rule, negative 1, the old exponent out in front, times t to the, now reduce the exponent by 1, negative 1 minus 1 is negative 2. So this would become simply 1/3, t to the 0 is 1, and then we'd have minus 1 over 3, and putting the t to the negative 2 in the denominators to get a positive exponent, negative 1 over 3t squared. This would be the derivative of our function t squared plus 1 over 3t. One more example. All right, this is the formula for the circumference of a circle. Let's suppose we want to take the derivative of c with respect to r. We want to find the instantaneous rate of change in c with respect to r. Remember, what we're doing is we're looking at delta c over delta r, an average rate of change, and taking the limit as the delta c, or excuse me, the delta r goes to 0. And we're letting that happen. And that gives us dc over dr, okay? All right, so dc over dr is going to be the derivative, well, taking out the constants, 2 pi times the derivative with respect to r of r to the first, I'll write the 1 for emphasis, which will be 2 pi times 1 r to the 0, and that's just simply 1, so this derivative would turn out to be 2 pi. Okay, all right, we'll look at a couple more examples in the next video.